Welcome to Rudy's Electronics Lab, and in our episodes of looking at the Rohde & Schwarz CMU200 as a generic measurement device, today we're going to look at its use as a power meter. Now, power meters are normally quite specialist types of devices. You have a number of different versions and principles depending on what exactly you want to do. And it's not very common that a power meter is to be found in the generic purpose type of instrument, but actually it is part of the CMU that we have over here. And not only that, we got a real average measuring power meter that is really wideband. Over the whole wideband of the device is diode based. We also got a frequency selective power meter where we can select not only the frequency, of course, but also some of the filter cutoffs that are used there. And we can also investigate measured power versus time in a graph type of thing. So a lot of interesting things to be discovered here. Before we get going, I want to take a quick look at power meters in general, what different types they are, for what they are used, and some of their most basic type of characteristics. If you're not interested in that, of course, you can fast forward directly to the part that's going to be specifically about the CMU. First of all, what are power meters being used for? Well, there's a wide range of applications. They could be product design or production facilities. It could be field measurements. It could also be real research. And as you see from these pictures, many of these things are quite high-end specialist type of task, and that we see reflected in quite a lot of power meters when it comes to their accuracy and the type of devices as they are. Now there are a lot of different power meters with a lot of different configuration actually on the market, and if you select any power meter, then you have to go through a number of considerations, and some of these considerations are basically what type of signal is to be measured here. Are we talking about a constant wave type of signal? Is this signal a pulsed signal like a radar or a gated signal? Are we talking about a modulated signal, analog or digital? And if digital, what type of modulation scheme is being used? And perhaps we're looking at multi-carrier signals, as we would find, for example, in a wireless cellular base station. Now, on top of that, it's also relevant to think about what type of measurements are being required. And it really depends on the type of the basic fundamental mechanism of a power meter where it's able to do particular types of measurements, as I will explain in a moment. So we might be interested in peak measurements, in averages measurements, or the ratio of peak to average. We might be interested in the average of a certain burst, which is being transmitted there. We might be perhaps interested in power at a specific moment in time for some gated measurement or for some slotted type of protocol. And we might actually want to investigate the envelope power versus time in a graphical manner. So these are all rather different things here. Now, let us look at some of the main parameters of these devices, and first I'll be talking about what way they're actually connected to whatever we want to measure in power. So first of all, we got the wired connection, the most common type of power meter, and that will be a power meter. Here you see a sensor for that, directly connected to the transmitter. So it acts as a sink. It consumes the energy of the transmitter. We can also have a wired connection where it's actually in the loop between the transmitter and the load, like an antenna. So that will be a reflection meter. For very high frequencies, we might actually be having a power meter connected by a waveguide. And in some particular situations, for example, in modern settings, we might have over-the-air measurement. An example here in case would be beam forwarding, which is something that is getting more and more important in modern mobile systems. And if you want to do power measurements on these. Now, next step that I want to talk about is the working mechanism, because they can be rather different. So first of all, I'll talk about the power meters that are based on diodes, and in their most simplest form, the simplified schematic diagram would look a little bit like that. would have an RF signal at the input that will be terminated by a load, typically 50 ohms. We have a diode that rectifies it, and then we actually have a capacitor there and measure the voltage of the capacitor, and then we digitize it and whatever with it. So these diode type of power meters, basically, they are very fast in terms of their measurement speed, and they have quite a wide measurement range. That might be typically for a professional power meter up to some 80 dB measure range or so. Should we wish a even wider measurement range, we can move to a multipath type of power diode, and there we would actually have 3 power diodes that are active at the same time, but they have different attenuations connected to them, and each of them is optimized for a particular attenuation range. And in some of these models, actually these 3 different ranges would have some overlap, so you wouldn't have a very sudden jump from the one to the other, but there's going to be an overlap area. I think in this example what we see here, the overlap is about 6 dB, where the results are the combination of both sensors. Now these have an extremely wide measurement range, can be up to 10 dB, or 90 dB, which is about 10 dB higher than a single diode. But these multipath type of sensors are not very suitable for very fast pulse signals. Now, a complete different family of power meters is based on a thermal process, either by a thermocouple or by a thermistor. So how does that look like? Actually, we would have the source heating up a resistor, the sink, which is a load of, for example, 50 ohm, and then we would have some element which is sensitive to temperature. That will be the basis of our measurements. And these type of devices respond to the true average power of the signal, whatever that is, a constant signal, a pulse signal, AM, FM, any complex type of modulation. So that's a nice feature. However, that's the only thing they can do. They can only measure average power, so we cannot do anything like peak or fast responses. They can have a very high accuracy, the highest of all types of power meters basically, and you can also get them to the highest frequency coverage. They're currently available, I believe, up to some 110 gigahertz. One of the downsides is their relatively poor sensitivity, so that means that there's a smaller measurement range, maybe something like 55 dB for a typical professional power meter, compared to the 80 dB we had with the diode and maybe 90 dB we could get with the multipath diode. And then finally there the reflection model as well, that usually work with the directional coupled port. That is another mechanism in itself, and there of course you don't consume the power of the transmitter, but you basically tap into it via via another line. Then sensors also differ greatly in their frequency range. I'm not going to go in details here, but here you see some pictures that you find in the product brochures of well-known manufacturers, Roden and Schwartz in the middle, and Keysight on the right. And you see they have a wide range of different sensors available, power meters available for all different types of frequency ranges. Talking also of frequency, we also have differences in bandwidth for the devices. Now the typical type of power meter actually will be a broadband power meter. So that will basically take a very broad frequency range that might be, for example, from 50 megahertz all the way up to perhaps 90 gigahertz. So that's an enormous range. And those equipped with a thermal sensor actually even might start at all the way down at DC. However, we also see power meters that are frequency selective, so they would pick out a particular frequency for which they will be measuring power, and that starts to look a little bit more like a spectrum analyzer, and the specific bandwidth within which they are able to measure might be, for example, up to 100 megahertz for a certain device. Then you can define anything smaller to 100 megahertz for the focal bandwidth, and it would ignore basically other signals around it. And for this type of frequency meters, of course, also relevant how exactly the filtering characteristics are for the in-band and the out-of-band signals. And then finally a little bit about the form factors. So we might have some generic instruments, and actually our CMU is an example of that. But to the best of my knowledge, there are not that many generic instruments that have something like a REL power meter that allows you to do average RF power built into it. The more common form of these high-end power meters will be base units that would have external sensors with it, and the external sensors basically ensure that you don't have a lot of losses over the cable and possibly other adapters, etc. in between. They might be both in analog and digital form, by which I mean that in the analog form basically the sensor would eventually deliver a voltage that is proportional to the measurement, and then actually the analog to digital conversion would take place in the base unit. While some of the more modern totally digital units, basically everything is happening in the sensor itself, including the AD stage, and basically the results are simply going to be sent to the base unit. So the base unit basically just provides control and displays. Such base units can often support multiple sensors, for example up to 4. And then the final category of form factors here is the standalone sensor, and that is a sensor where the output, the measurement itself, is delivered by a USB port, or in some cases with a LAN interface. So using power over Ethernet, you could kind of put these sensors like far away. They may even include a web server that you remotely log into it, and the whole device is then self-sustained. So this is great, for example, if your power meter is hanging somewhere up in a transmission tower or so. Now, I covered just a small number of elements of the power meters. There's much more to look at. One of them, if the sensors can be gated, are suitable for time slot measurement, whether particularly suitable for pulse measurement, like for radar, the amount of power they can handle. Some of them can handle powers up to 45 dBm, and certainly the reflective ones, those that go in line basically, can sometimes handle up to 150 watts of continuous power. So it could even be put on a permanent basis in the installation. They also differ in the number of readings they make and the number of measurements per second, in the noise floor, and some of them also provide capabilities for S parameters measurement or even correction, where basically the characteristics of the cable or adapter or anything in between could also be considered when measurements are being made. Now, we saw some very cool modern meters here, but let's get our feedback on the ground. Let's look at the CMU200 in its use as a power meter. And so the interesting thing is that it has a real wideband power meter measurement, and that is realized by a diode setting that is in the RF front end. And in my last video I discussed in much more detail exactly how that looks like. It's a peak detector unit, and here we also see a little bit of the schematics being used there, where we see the diode, and that is a power meter with a 41 dB range. And then we can also do frequency specific power metering, and that actually uses the same circuit as the regular spectrum analyzer in the device uses. So it has a much wider range, but of course it's not going to be wideband. Now, I think it's an interesting power meter. In a moment we're going to look at it more detail how it works, but I think it's always important to keep in mind what is the particular device was being designed for, and that was for actually testing mobile communication devices. So I don't think it's fair to compare this with a dedicated power meter like we saw on the picture before, but nevertheless, like I said, we have here some power metering capabilities that are not present in a lot of general purpose type of devices. Now, how is the power meter being implemented? It took me a little bit of time actually to really fully understand it. So let me try to plot it out for you. So first of all, there's something which is called the power meter wideband, and that is something we see in the connection control menu. It also got a bar graph function with it, and that is really a wideband power meter based on the diode setting. Now then we have a second part in the device where we find the power meter, and this part is called the power analyzer. It had its own menu here. Now, if we're in the power analyzer and we configure the resolution bandwidth as being wide, then actually we get exactly the same power meter as we had in the previous block here, with some small difference in terms of the resolution of the measurements that are being shown on the screen. However, if we put the resolution bandwidth at any other value, we basically get a frequency selective power meter. And in this case, we can set the resolution bandwidth somewhere between 10 Hz and 1 megahertz. I think it goes in 1 to 5 steps if I remember well. And we have to set then, of course, a frequency that we're interested in, and that can be set over the range of the whole device, which is 10 megahertz to 2.7 gigahertz. Then there is a menu in the device which is called Power Meter Frequency Selective, and that's the more advanced one. Also here we set the frequency, we set the resolution bandwidth, again between the values that I mentioned before. But here, so we have also possibility to set the resolution bandwidth to TDMA and CDMA, which are specific values that align with mobile telecommunications standards. And we also, in that respect, have a number of filters there, not only Gaussian, but also filters that are particularly defined in the US TDMA standard and in the wideband CDMA standard. So we can properly determine the in-band power and the out-of-band powers within these signals that we're measuring. And we also got a couple of statistics functionalities here. And then finally, the last part of the implementation in this device is what is called power over time. And then we're actually looking at something with a time graph, with a curve over time. And again, we can set here the focal frequency, we can set a resolution bandwidth, a variety of detector settings and display settings, and we can also show statistics. Now, here you see our setup for the wideband power level measurement. So we got here is a 2 watts unit maximum, a 50 watt unit, and we'll be starting with that one. And then, of course, since we want also to test the 50 watts, we got a signal generator here. Actually, we got a ham radio here that can deliver all the way up to 100 watts of power. And since this one is loaded by 50 ohms, the input impedance here is 50 ohms. There's a dummy inside. It's actually be able to deliver its full power into that. So the first thing we'll do basically is go to the ham radio here, and because we don't want to run full 100 watts, that would be too much, and we can basically set the RF power to a lower level. So I'll start here with 2%, which should be roughly like 2 watts, and we'll be measuring what it is going to be exactly. Yeah. Secondly, right now it's set on amplitude modulation, but then the actual output power will depend on the amplitude of the audio signal. So what we'll do is that we'll go here to an FM signal, so we have like a constant carrier once we turn on the transmit of this unit. Now let's first then go to this unit, the 51 unit, and configure it for measurement. It's in basic functions, it is in RF. We go here, and we will get to the normal menu, and we can go to the control connect control menu, where we can select the inputs and outputs. As we can see, little LED indicators right here. RF3 is selected for output. We're not going to use any output right now. RF2 is for input, so we got to change that. RF2 input. We'll go here and we'll make it RF1, which is actually the port that can carry the highest amount of power in this unit. Now I'm going to do wideband power measurement, and the wideband power measurement is going to be shown right here already in the connection screen. It's also shown on another screen for the broadband, the wideband power analyzer, but it's also shown here. And I think the reason for that basically is that they want you to be able to see the power level right away into this menu, whether a signal is present and whether it will be overloading the unit, and whether there's any reason to use attenuation settings or otherwise, which is fine. And so the next thing is, even though we're going to do power wideband measurements, the manual actually explains that it's a good idea to set the frequency in the analyze menu anyway to the frequency that you're going to measure, because then apparently the accuracy will be higher. So I'm going to try to do that. I'm going to go to the menu here, which is the application menu. The frequency is already right here, and I'm going to change that to 50 megahertz, which is the frequency of my my ham radio here. And I'm going to go back to connect control. Well, now basically my setup should be ready to go and measure. Again, this unit is set at 2% of the maximum power, so I have approximately 2 watts. So I would be expecting to see here a dB level that would correspond to 2 watts. So let's go and turn the transmit on. And what we're getting here is 31.3 dB. And I think that's about 1.6, 1.7 watts or so. I'll later on put it in the calculator and I'm going to show it on the screen. So that looks like fine. It's slightly below the 2 watts, that will be 2% of 100 watts, but I don't think this is very precisely calibrated in terms of these numbers. So I have much greater confidence in this unit here. So let's trust that we're at 1.7 watts or so right now. And then we should be able to bring it up and see what higher power levels, because as is already suggested here basically by the little bar, there's still some margin to go up in power. So let's go and see if we turn this to 10% of its transmit power. We're at 39.3 dBm, which is 8.5 watts of power, I believe. Slightly under the 10 watts, 10% of 100 watts, but again, this is probably not very precisely calibrated. And then we should be able to go all the way up without any problems to measuring something close to 50 watts. So let's bring up the output power here. We're transmitting now at 50 watts. All of that is dissipated right now in this unit. It's not getting terribly hot yet. I can also see it from the display here. What we're getting, 47.1 dBm, which is actually equal to 51.3 watts. I checked it in the calculator before. Yeah, so without any trouble we're able to measure 50 watts. To be very honest, I don't think everybody will agree with me, but I would appreciate it if they simultaneously would have shown here the power in watts and milliwatts as well. I mean, they do it on the input connectors. They could have done it here as well. It would save us from having to use a little calculator all of the time. But altogether, I'm happy here. I'm happy to see that we can basically see the power, and we still got some margin. We could still be going up here before we get into error messages. I'll go to 60 watts. Yeah, I'll be stopping here. I don't want to burn the unit or go above its specifications. But so altogether, it's easily able to measure the 50 watts that's supposed to be able to this particular unit here. Now, like I said, we're here looking in the Connect Control menu. There's also a dedicated application for looking at wideband power levels. So we would go there basically to the power meter menu here. And right now we're selective and we go to wideband, and we exactly get to see the exactly same type of measurement as we get over here. Actually, we see it in a slightly higher resolution. We see 1 digit more. I believe this one still with the one on the Connect Control menu will be on the one of the power diodes that are right away into the input unit of the device. Now, of course, we want to see as well how the 2 watt unit deals with that. So let's turn off the transmission power. It was still on 2 watts, I believe. Let me double check that. Yeah, we don't want to blow this unit, and I'm going to connect it to the other unit here. Okay, I must admit that the type of cabling I'm using is far from perfect for the type of powers here, but I don't want to waste any of my good measurement cables over here. So I'm not sitting very properly in front of the screen, so there we. Okay, I'm messing this up a little bit because they're both turning. No, well, it's fine as it is. Okay, let's look at this unit here, the 2 watts unit. Again, I'll go to the right functionality here. So I'll go to the analyzer menu. I arrive in the startup. It's already RF1 being selected. And like with the other unit, let me just set it to the right frequency here, like is recommended. I'm going back here. I got it connected to RF1. I see the right input here. So again, let's turn on the transmitter. And we're getting to see, yeah, again, 31 dB. So this is what we also expected. That's what we saw on the other unit as well. But of course, here we're already at the upper bound of its measurement range, because this is the 2 watt unit. And we can already see that here graphically as well in this indicator here. So we might be able to go a little bit up here. And
overload the unit slightly. Yeah, so at 39 dB I get an overload condition here, and 39 dB, that should be equal to something like, well, approximately 9 watts already. Then it gets into overload. But this is to be expected. This is the 2 watt unit here, so we cannot expect it to deal with 50 watts like the other one. But anyway, the wideband power seems to be measuring well here on all the devices. In the next experiment, I'm going to measure the frequency specific power meter, and I'm going to use the unit over here. The incoming signals here are coming from the Siglent signal generator here, and I choose that one instead of the SMIQ that I used in earlier episodes, because this one can easily generate 2 different tones at the same time and combine them at the output. So I'm going to combine the tones of channel 1 and channel 2. Let us take a quick look at how this unit is configured right now. So on channel 1 I got a sine wave of 30 megahertz. On channel 2 I got a sine wave of 34 megahertz. Both of them are very weak now at minus 10 dB. And I'm going to combine these 2 waves via the utility output setting wave combine menu. And as you see here, I've already preset it here, is that output number 1 is basically getting the addition of channel 1 and channel 2. And that's what I want here basically. So now let's go and see these signals on the CMU device. So I'm going here basically to the analyzer menu. I got the right inputs selected. Like I explained before, it's advisable to set the frequency already to the expected frequency range. Now 30 megahertz, that's fine. And we're going to boost our signal. As you can see, there's nothing yet being detected. The wideband power meters are not very sensitive. They will come in right here at 1 dB or so. Sometimes we see a short overload condition. That happens more often at the device. I'm not worrying about that. The device should be able to handle 50 watts or so, but sometimes we get this power overload. Okay, we got rid of it. I think it needs to set it itself. Now I'm going to send in a signal of 5 dBm here, and in the wideband meter this is recognized at 4.8 or so. Now that's perfectly possible. I might have some cable losses. Maybe this unit is not perfectly calibrated, or the CMU, but I would say close enough. Okay, now I'm going to add a second signal here, and so I would expect here this level to go up. I'm changing to channel 2. I'm also going to increase that one, and I'm going to bring it at, let me see where I'm going to set it, 3 dB. So I'm sending in 5 dB tone and a 3 dB tone, and I measure 6.9. Now we have to be careful here. We're talking here of dBm, so we cannot simply add dBms. You cannot say 5 plus 3 is 8 and we're getting a wrong measurement here. Actually 5 plus 3 dBm, we best translate it back to the regular power domain in watts. Then we add it up and then we convert it back into dBm, and so it's 7.1 the correct value, and not 8. And we're measuring 6.9, which is fairly close to 7.1. Again, we might have some cable losses or imperfect calibration of the devices, but again I think this is very close. So we're satisfied with the wideband power meter is telling us. But of course we're doing this experiment to see something about the selective power meter, so let's go there now. We're right now in the power meter selective menu. Here we can still move to the wideband meter specific screen and the power meter here. And so what we're basically going to do is that we're going to check here the bandwidth, resolution bandwidth. I think 300 kilohertz is fine for our application. We go to the frequency menu, and what I'm going to do here is basically I'm going to walk through some frequencies and see if I see the 2 tones that I expect here. So basically 28, almost nothing at all, 29, 30, and we nicely see here the 5.80 dB. It's even slightly more than the 5 dB that I said there. Then again, nothing at all, nothing, nothing. And at 34 again, we see our 3 dB coming in. Yeah, so yeah, that basically means that this is working fine. He's picking up right the two different signals at the frequencies where these tones are present. And this is how the frequency selective menu works. And as you might have guessed, this method here basically is much more sensitive. So here, if we go to much lower values, let's just go to something like I don't know how low my unit is bringing me here, but minus 30 dB. Yeah, so we got minus 30 dBm. Sometimes I say dB, but it's dBm, of course. We're working here in power levels, not relative levels. Yeah, so far the selective power meter is functioning just as you would expect in the CMU. So the last experiment I want to do today is carry out the power versus time measurement in the CMU, because I think it's one of the more interesting possibilities this device offers in this domain. And I think originally this function is designed really for analyzing protocols that have short signal bursts. And I'll show you an example here of a GSM measurement carried out by actually the same device that you see right over here. But since we're today looking into using CMU as a general purpose type of device, I will actually do some other experiments, and they will involve the two little units that you see here on the top. These are little LoRa transceivers. They are based on Arduino and a LoRa board on top of the Arduino. And then I added here some little board with some LED lights on it. And so the way this is working basically, that this unit is sending out a signal, then is waiting for some expected response from another unit. If that response doesn't arrive, there's a timeout and there's a little red light blinking there. However, if the response is received, then we should see a green light. And the response is coming from the second unit here. I'm going to power it on right now. There we go. And you see it powers on very fast as an Arduino, so super fast boot time. And what we see now is actually after the message transmitted, received by the unit over here, the unit there sends it back, and we see a confirmation of the reception of the accepted message. This works in the license-free band 868 megahertz, the regulatory band in which you can use devices like this. And deliberately I've reduced the transmit power of the unit over here a bit. Actually, I did so by putting a attenuation in the antenna chain. Now we're going to use the CMU, of course, to analyze the signals here, and we're receiving the signals with this antenna over here. This is an omnilog, omnidirectional antenna. Actually, an antenna I like a lot. I'm using it a lot for my experiments. What I'm going to do is actually I'm going to turn it downwards here, so it's not in the way when I'm using the unit right now. Now let us see how we can analyze the power in this scenario. And well, today's purpose is not to play around with the spectrum analyzer, but I will quickly go there anyway, and we'll take a quick look at it. The spectrum analyzer, we got it here, and we see very shortly signals coming in here. They're fairly short signals. We kind of see also two different power levels here, but with just a regular spectrum analyzer, even though the picture is refreshed fairly often, we don't really get the time of insight in terms of the power levels of these two devices here that I would like to look at. So let's go back to the possibilities that the power analyzer over time offers here. So I'm going there now. This is the menu for it. This is that we see that the application is running. And what we see here basically a time domain and sometimes a jump to a higher power level. The thing is that, and it's not receiving my signal, maybe the attenuation is even so much that it doesn't take. There we go. Yeah. So we also kind of see two different power levels. But of course we would like to study the burst a little bit more into detail. And how do we do that? Well, actually by first trying to trigger this signal on the burst in question. And how do we do that? We go to analyzer settings. I should have mentioned before that I've already set this analyzer in advance on the right frequency. You need to specify a frequency, otherwise it won't work. And also a resolution bandwidth that I've already set in advance. Now we see the device now triggering on free run, and we got a couple of trigger options here, which is also on RF power, on EF power and external. And the external part, now it's frozen, the screen. That comes in via the aux port here on the front, and I made a little adapter cable to make it a little bit easier to connect to stuff. But right now I will be using the EF power here. Yeah, actually there we go. We got the device here, and it's triggering now. Yeah, and we see it refreshing, and so we see the start of the burst here. Well, ideally we would like to see the full burst, and in order to do that we can go to the display menu, and if there's a little yellow thingy here, then that actually means there are two different menus here. So this is the regular marker menu. We'll look at that later when I'm going to investigate the spectrum analyzer. But we also have here the secondary menu here, and that is actually time scale. So we got the level scale, so that is the vertical level, how many dBs. We got the time scale start, and this is the start relative here to the trigger point. So it's a negative value, it means that we see a little bit of the value before the trigger point is coming in. And we got the time span, and that's what we're interested in. And so if we decrease the time span, we can actually see that also happening here with the divisional lines here on the screen. Make it bigger and bigger. And then the thing is that we're at the maximum level here, and we're not getting the complete burst yet. So what is going on? Well, the actual setting here is that we cannot go beyond this 9,000 milliseconds, so 9 milliseconds. And I think that is per division on this unit. So the burst of this is fairly long, and I think the device, the CMU, has been designed for devices measuring stuff with much shorter burst time, like telecommunication protocol. But this LoRa thing is fairly slow. That's the way the radio protocol of LoRa was designed, for deep penetration, etc., but not necessarily for speed. So we cannot really look at that. However, we can do a thing which I think gives a little bit more insight in what we're doing here, and that's going back here and put the trigger level to the falling edge. Let's go back to the display and let's have the start point a little bit edited. Okay, that goes very slow. Let me use the yeah, there we got it. So you can see it's still triggering. And so what we see here is actually, we see the last part of the burst of the sending signal. We see the short delay in which before this unit reacts, and then we see the reaction of the other unit. And now we can perfectly see basically the levels, which is about minus 20 dB for the transmitter, and it's about minus 40 dBm. I always say dB, but it's dBm of course here, relative to power, for the other unit basically. And we see it going up and down a little bit, but that depends on basically whether I move my hand here or not, because that attenuates the signal slightly. So I think this gives you a kind of an idea how this function of power versus time works. Even if we can actually not set it for very long time scales, I would prefer if we could set it to tens of seconds or even full seconds basically to look at the development of power over time. Nevertheless, you can work around it a little bit, and I think it's kind of a useful way to further investigate RF signals. So now, as the last part of our power measurement test, I want to look at power domain or time domain power measurement, as it's called, power versus time in the device, because that's, I think, one of the interesting options that is being offered here. So let me first explain you what experiment we're going to do. I have two little units here that I built myself. Well, actually this is a standard LoRa unit built on a Arduino. And I wrote a little bit of code of it, and I wrote a little I/O board with a couple of lights on it. And what's happening here is it's sending out a LoRa signal, and then it's waiting for a kind of a known reply from the other side. And if that reply never gets there and we get a timeout error, then the red little light will turn on, as you see happening right now. I'm not sure if the lights come across well in the video or not, but this is yellow, green, red, and there's another red for error condition. Now, if there is actually a expected reply, which is going to be sent here by this receiving unit here, that's going to send back the reply. I'm going to turn it on here. Oops. Yeah, and it boots very fast. It's an Arduino, so it's very fast. And now we see every time that the green light lights up as a confirmation that the reply is being received. So what we see very quickly, transmit, then a fraction of a second later, there is a confirmation of a write receive signal from the unit over there. And deliberately, I have decreased the RF transmit power of this unit a little bit, actually just by putting an attenuator in the antenna chain. And this is all working at 868 megahertz, which is of course one of the allowed regulatory bands for the use of LoRa units. And I'm going to pick this up with the CMU. I'm going to use this antenna here. This is an omnilog antenna. I use it for a lot of experiments. It's a very nice omnidirectional antenna. I'm just going to have it facing downwards, so it's not in the way, but so you know it's still being connected here. And although this episode we're not going to focus basically on the spectrum analyzer, let's take a quick look here. Anyway, we got the spectrum analyzer running here. We got it at 868 megahertz center frequency, and we can see, yeah, with some regularity there is a signal coming in. And if we look well, we might even see that sometimes we got a weaker signal and sometimes we got a stronger signal coming by. I would like to make a little update. Earlier in my video I said that you cannot increase the time period over which you were looking at the burst above a certain level. And then I think I was at 10 microseconds if I was right per unit. But no, you can do that. Actually, I was reading the manual on this, and the manual says that time period is basically depends on the selected bandwidth. So basically, if we go in the device to another resolution bandwidth option, we should be able to choose a longer time. And as a matter of fact, we do. So what I actually managed here is to get like the full burst of the first unit and then almost the full burst of the second unit in view. You can even look at a longer time period. It comes at a price, however, because if you choose like a resolution bandwidth as small as this, what you're basically getting is more and more noise. You can see it happening here. If the bandwidth is high enough, then I get a nice signal. But it does get distorted at the moment that I make it shorter. So yes, I can get a little bit more understanding of my signal, but at the wait, I'm in the wrong menu here. I wanted to turn back the time scale. But at the expense of a strongly distorted figure. Yeah, now we get the whole pulse even, but this doesn't make sense anymore. We got too much distortion. But if you're willing to live with some distortion, you can have a better idea and also make measurements about the length of certain bursts, using, for example, the possibilities that we got here with reference points and markers that we can put here. So, what can we conclude about the CMU as a power meter? So, I think it's got a couple of quite interesting features. It can handle all the way up to 50 watts directly into the device. That is rather unique. Also the fact that it's part of a generic purpose instrument that you might actually purchase for its other functionality makes it really attractive that it is there. And it has a true wideband power meter, diode based, in addition to the functionalities I also discussed in the video, like the frequency specific power meters with specific filter settings, as well as measurement power versus time. Can you directly compare it to the high-end instruments that I showed in the beginning of this video? No, I don't think that will be fair. It doesn't have the precision of those instruments that are often way below 0.5 dB. It doesn't have the frequency range up to 50 or 100 gigahertz or something. It doesn't have some of the very specialized type of features that come up with these devices. It doesn't have the dynamic range that we see in some of these professional high-end devices. But nevertheless, I think it is very interesting to have this functionality on the CMU, and I hope this video was useful for you in some way. Soon I'm going to look at other features, generic measurement type of application for the CMU, and also going to look at it using it as a spectrum analyzer. We're going to look at it as using it as a signal generator, and we're also going to play around a little bit with the audio analysis possibilities that this device offers. But that's for another time. This was it for today. Thanks for watching. See you next time.